Today's lecture follows on from last week. We're going to start Module 1, and Module 1 is about aerospace materials and their properties. So there'll be 3 lectures for this module. The first one is a generic aerospace materials lecture where we'll cover everything that's not composites. We'll have a lecture next week on solid mechanics, so going one step further and looking at how we can predict stresses and failure in materials. And then the third lecture we'll talk about composites. Composites being a combination of simple materials to make something a bit more complex, and as a result they've got a little bit more complex analysis behind them, so we'll leave that for the last lecture. Okay, give me 1 second here. I need my presenter. Okay, so let's talk about engineering materials. So can anyone name any materials or classes of materials that we use in engineering? So I mean, you all have walked around and seen engineered things, buildings, cars, aircraft. So metals, okay? Metals, ceramics. I heard carbon fibre in there. Fibre. So this, in general, we would call composites. Okay. Plastics, which we could also call polymers. Okay. We could also call metals more generally alloys. Okay, because we generally use some alloy of different materials. We don't tend to use just a metal that's straight off the periodic table. We tend to use some alloy of multiple materials. Okay, so that's a reasonably good range of materials. So metals, more specifically, the more common ones you see around steel, titanium, aluminium in our case with aircraft. But we'll talk a bit more about that in a minute. So what about terminology to define properties for materials? So if we were to say these are the kind of materials we would use in engineering, what kind of properties of those materials are useful in engineering? Yeah, so strength. Strength. Stiffness. Cost. Yeah, cost is a tricky one because there's raw material costs, there's processing and fabrication. So there's a lot of issues in cost. It's a very tricky thing to quantify. The amount that it costs to get out of the ground is, in the case of a metal, is very different from the cost of actually using it. What about other engineering properties? Mass. So I'm going to write density, just because I'll talk about density a bit in a minute. Okay. There are other things too. Corrosion resistance. Okay. There are things that we roughly would call toughness. Okay, so unlike strength and stiffness, toughness refers to how much energy a material can absorb before it breaks. So materials can be strong, but they can be brittle. But materials can be strong and can also be tough, but it's a separate material property. Okay. There are also some other things which are indirectly related to engineering materials, and they probably come into cost as well. Manufacturability. Manufacturability. Sorry about my small and horrible handwriting. But when we talk about different materials, we also have to talk about the kind of processing we can do to them to allow them to be used in different ways. Manufacturability actually has a big impact on how we use engineering materials. There's a few others that we'll get to in this lecture. Okay. What is the goal of when selecting materials for aerospace structures? What are we trying to do? I mean, if you said to somebody, I need to design an aircraft to fly so many people from this place to that place, go and design me an aircraft. What's the end goal?
Low weight.
Yeah, so I'll chuck that one up there. Okay. But what does low weight give us in the end? I'll put low weight up here. Okay. In the end, low weight and efficiency are less fuel burned. Okay, so if we bring everything back to the end goal, which is generally an economic one, it doesn't always have to be an economic one. This can also be related to performance as well. If our aircraft isn't designed to be a commercial vehicle where we're transporting people or goods from one place to another, if it's a military vehicle or if it's an acrobatic vehicle, for instance, low weight can contribute to the performance. So often the metric for our vehicle is not how much fuel it burns, but how well it can perform a specific task. Okay. All right, are there any others that you can think about?
Having a structure that resists damage, like if you had
Yeah.
a lane or whatever.
Yeah, so damage tolerance, fatigue tolerance. Okay, so things that relate to the lifetime of the aircraft are very important. So things that extend the period between inspections, things that increase the life of the aircraft are very important. So not only are we talking about its performance in the short term, but also its performance in the long term. Okay. Okay, so those are really the two main drivers for most aerospace materials. And we can break them down into near infinite permutations, but really in the end we're trying to make the aircraft as a whole lighter, burn less fuel, increase performance, and also have a reasonable lifetime that's dependent on the mission that the aircraft has been selected for. And we'll see towards the end of this lecture that you have to determine the mission of the aircraft before you can decide the materials that it's made out of, because the mission will very much drive the types of materials that we're going to use. Okay. So this is a selection of aerospace materials. Up here, we have steel, okay, which is at the moment it's just steel rebar from a picture from a civil engineering structure, so it's not really in the form that we would use on an aircraft. Aluminium up in the top right, carbon fibre down the bottom left, polymers and plastics, and when you mix carbon fibre and a polymer you get a composite, which is what a lot of aircraft these days are made out of. And we have titanium in the middle, although it's very hard to find a useful picture of titanium. It tends to most metals tend to look grey when you take a picture of them. So it's hard to define a defining picture of titanium. Okay, so the big question, and it's one that I asked you to think about during the week, the big question is, steel is used everywhere in engineering. It's civil engineering structures, automotive, trains. It's got a great set of properties. It's very cheap. We produce tons of it around the world. Weldable, strong, has great specific strength and stiffness. Why is there basically no flying steel other than from a few bits on the aircraft? Why are most of it? Sorry? Is it too dense? Okay, so this is something I'm going to challenge some of your preconceptions here. Okay, so let's just talk about this. Okay, So density is one thing that's often raised, and I'll show you some stats here. Okay, let's look at a selection of materials, and up in the top left we have aluminium 2024 and 7075, which are two common aerospace alloys, and underneath we have some steel properties as well, and this is in Imperial units, which I will use a bit in the tutorials for this lecture because Imperial units are kind of important for a lot of aerospace engineering. Now, if you look at FTU, stands for the stress tensile ultimate, so maximum tensile ultimate stress. FTY is the yield stress in tension, and CY is the yield stress in compression. Okay, and E is stiffness as usual. Now, aluminium has a yield stress of 42 KSI, and some of the steels are 150 or 230. So that's a huge difference, and aluminium is a modulus of around 10, and steel has a modulus of around 30. So how much denser does steel have to be than aluminium to make it a viable option, or how much denser does steel have to be before aluminium comes into the frame? Well, if we add density into the equation and we look at the specific strength and the specific stiffness of these materials, which is the strength divided by the density and the stiffness divided by the density, we can compare materials on a weight-for-weight basis. Now, if we look up here, if we look at the specific modulus, so the Young's modulus divided by the density, steel, 105, 102, aluminium, 107, 102. Okay, there's basically no difference between the modulus. And strength, steel's potentially even a bit stronger specific strength. Okay, so when you say steel is too heavy, well, even when you divide by the density, steel is still stronger. Okay, so if you wanted to do a weight-for-weight comparison where you had the same strength piece of material, the steel one would be lighter than the aluminium one. Okay, so the argument about density, it's partially true, as we'll see in a minute, but it's not completely true. And just before I get too far off topic, I'm going to talk a bit about some materials, Imperial units, okay, just so that we can interpret some of the units we're using. Okay, one of the benefits of the Imperial unit system is that mass and weight are measured in the same way. Okay, when in the SI system, when we get on a set of scales and we say that we weigh 85 kilograms, for instance, we don't actually measure the mass. We measure a weight, and the scale is calibrated to divide out by gravity as part of what the scale does. It automatically divides by G to give you a mass. You can't measure mass with a scale. Whereas in Imperial units, the G is built into the units already. So when you say something weighs 500 pounds, that implies that it has 500 pounds mass, and it also has 500 pounds force applying on the ground. So pounds, when you see it used in a set of units, you can automatically assume it's a force and everything's okay. So the force that we use is in pounds, or LB. Okay. The length unit, okay, just like in SI we might use meters or millimeters, the length unit can be inches or can be feet. Okay, we very, very rarely would use a yard, but in most cases it's inches and in feet. For solid mechanics purposes, it's normally inches because we're talking about things that are measured in smaller units of area. For measuring dimensions of an aircraft, we're normally using feet because it's just easier to say 200 feet than it is to say 1,300 inches or something along those lines. The units are a bit easier to measure, and I didn't do that multiplication correctly in my head, so don't quote me on that. Okay, so stresses, so anything to do with a stress, okay, what's the basic, in SI, what can we equate stress to? Stress is the same as a pressure. It's a force per unit area. Okay, so anything to do with a pressure, we tend to use pounds per square inch, which is normally written, even though pounds, the symbol for pounds is LB, is normally written as PSI. It's confusing. And because we don't tend to have things that are in the right orders of magnitude to use PSI, we use multiples of that. So 1,000 PSI is 1 KSI, okay, and that's a kilopound per square inch, or a kip per square inch. Okay. And 10 to the 3 KSI is equal to 1 MSI. Okay, so it's the same set of K and M that you'd be expected to use in SI units. So when you see KSI, it's a kilopound per square inch. And the other name for a kilopound is a kip. So kilopound per square inch. All right, so let's do a little example to make sure that we understand what I'm talking about on this slide here, that steel is actually stronger than aluminium. Okay. So we'll do an example. So let's assume we've got a steel rod and an aluminium rod, and we want them to be the same strength. We're going to measure how much they weigh. So we get our steel rod, and I'm drawing the aluminium one bigger because I know that the density of these two things is going to be different. Okay, and we'll give this one a cross-sectional area, A steel, A aluminium, okay. Now let's just compare say we want both of them to be able to carry 1 kip. Okay, how do we go about determining the cross-sectional area of each one to be able to do that in tension? We'll say we're working on yields. We want it to not yield at 1 kip, so not to fail, but we don't want it to yield at 1 kip. So how would we do that? We've got the yield stress of the material here, so we'll call it aluminium 2024. Okay. So this bar is 2024, and we'll call the steel 17 7pH, which is just a particular type of steel. So, stress equals force over area. Okay, so the critical stress at which something's going to fail, is equal to the critical force over the cross-sectional area. So if we want our bar to be able to take 1 kilopound, and we know the stress at which it's going to yield, which we've got up there, we can work out the area. Okay, so what I want you to try and do is work out the area of this steel bar to take 1 kip and the area of the aluminium bar to take 1 kip. And I haven't run this with this set of units before, so I'll just see. We might get a silly answer. Things might be too small or too big, but I assume it's about right. Okay. So if we look at the units up here, we want to be using, sorry for the camera guys, but we want to be using this column here, which is the FTY column, the tensile yield strength. Now if we've got kilopounds on the top of the equation and we've got kilopounds per square inch on the bottom of the equation, what's the answer going to come out as? Square inches. Yeah. So the way I've drawn these, we're probably going to end up with sort of wires rather than rods, but if you've got an answer, throw it out there. The only way we find out whether we have got the right answers in this class is via democracy. I'm never going to calculate them myself up the front. So throw out an answer, and if everyone agrees with you, then you can get the credit for being right. Otherwise, we'll shame you all. No, it's no. Just throw out an answer if you've got it.
Isn't it just 1 over each of the FTY properties?
Yeah.
So I know the first one is 0.00666.
0.007, I'm just going to say, because we're going to just round off there. 7.
For steel.
Oh, for steel, sorry. Is that for steel? So 7 by 10 to the minus 3 square inches. Okay. And the aluminium.
0.023. Or 0.024, sorry.
So 24 by 10 to the minus 3 inches squared. Okay. Now, let's assume that each one of these, so these are wires basically. They're not rods, but let's just assume that we've got, say, what's about a meter? Say 40 inches of each one. Now, which one's going to weigh the least? So if we want to work out the weight of each one, so to get to weight, what do? We take the cross-sectional area times the length times the density. So you've got the density up there in pounds per cubic inch. So we can work out the weight of each rod. So let's say we've got 40 inches. Another way you'll see inches written is you'll often see 2 inverted commas or doubling inverted commas for inches. A single inverted comma means feet. 0.074. Okay. I'll talk about significant figures at later on, but I'm a bit of a stickler for putting too many significant figures on things. It's very easy to turn something that actually means something into gibberish by putting too many decimal places after it. So the weight of this one is 0.074 pounds. And what was the weight of the aluminium? 0.095. Okay, so the steels are lighter. And it's not a surprise, I already told you that was going to be the case, but this is why, if you've got cabling on an aircraft, if you've got anyone with a mechanically linked control system, which is most light aircraft do. They have cables to control from the stick to the control surfaces. That cabling is not made out of aluminium. That cabling is made out of steel because it's lighter. So everything in tension is great. The steel is much better than aluminium. The problem comes when we flip that around and we try and apply a compressive load to something. Now if you think about these two bars, okay, aluminium is less dense, so for a given component that's loaded in compression, if we wanted to make them the same strength in tension, the aluminium part's going to be thicker. So with a cable, the cable's got more cross-sectional area with aluminium, but if it's a sheet of metal, for instance, then that sheet of metal, if it's aluminium, is going to be thicker. Now, the thickness actually gives us a really key advantage when you load in compression, because when you load in compression, things tend to buckle. They tend to displace out of plane, like last week I showed you with the bit of paper. The thinner something is, the more prone it is to buckling. Okay? And even though the stiffness of the material plays a role, the biggest factor in that calculation is the thickness. It's a t squared or sometimes a t cubed effect where the thicker something is, it gets a much higher buckling load. So the reason we use aluminium is because large chunks of our aircraft are loaded in compression. When you load a wing up, the top surface is in compression and the bottom surface is in tension. So if we made it out of steel, the top surface of the wings would just do this, okay? Because the steel would be too thin. What happens when we use aluminium is we actually get an increased local bending stiffness, which gives us the ability to take loads in compression. And it's the primary reason that aircraft are built from aluminium. Okay, so it is because aluminium's lighter, but it's not because it will give you a lighter aircraft because it weighs less. It's because it gives you thicker skins as a result. Okay. We don't use aluminium just because it's light. As we've seen here, if we did a pure weight for weight comparison, steel still beats aluminium. Okay. Now, aluminium has a lot of downsides. It's not the easiest stuff to work. Okay, most of its strength comes from heat treatment. So because most of its strength comes from heat treatment, we can't then go and weld things, because as you weld it, you change the local heating and everything can lose its strength. Okay. So we normally, with aluminium, have to heat treat something, form it into shape, let it cool, do some potential sort of after forming processes to get the maximum strength out of the material. And so it's tricky to work with. It's not as easy as steel where you can just go along and weld up a structure and you'll get a pretty good outcome. Aircraft are not welded. They're always fastened or bonded. You never see an aircraft mechanic out there with a welder welding something on. All right, so that covers that question I was asking last week about why we make aircraft out of aluminium, and we'll see in a couple of weeks' time when we talk about composites. Composites take that one step further. So composites are even less dense and have even higher specific strengths and stiffnesses, so it drives that calculation even further into the direction of using composite materials. So there are other issues with composites that make them trickier to use, and it's why they're only now coming into aircraft, but we'll talk about that in a couple of weeks. So for the next little while, I want to talk about the aging of aircraft. So there are different mechanisms by which aircraft age. And we'll talk about 4 different mechanisms. Okay, so what happens to engineering materials with time? And by this I mean engineering materials in service. So something that's being used in service. If you were to come back to a part it's being used 10 years from when it was made, chances are that it's degraded from its original condition. And we have 4 different ways by which it can degrade, which we'll talk about, but can anyone have a go at naming?
Cracking and corrosion.
Okay, so cracking, so we'll call that one fatigue. And we'll talk about fatigue more specifically in a minute. Corrosion. Wear. And anyone who has the notes can cheat, I suppose. And there's one more, which is not so much of an issue for aircraft, but it has played a role in the past. Okay, the last one's a bit tricky. It's creep. Okay. If you load a material up statically, if it's got an elevated temperature or if it's the right kind of material, it can actually stretch and break over time without, it won't break immediately, but if you leave it for long enough, it will stretch and then fail. So all of these have some role to play in the lifetime of our aircraft. Primarily, these two are the thing that drive how long we can use our aircraft for. Wear and creep are less common. Okay, so we tend to treat these quite locally for specific components, but fatigue and corrosion are things that occur everywhere on the airframe. We can't avoid corrosion and we can't avoid fatigue. We just have to have strategies to mitigate against them. So I'll go through them individually. So fatigue. So can anyone tell me what this aircraft is? Comet, yeah. So if anyone who's done any kind of aerospace history, we really learnt about fatigue from an aerospace perspective through this aircraft. And the reason we learn about it through this aircraft is because a bunch of them fell out of the sky in bad weather, and it was a revolutionary plane for its time, and everyone thought it was the greatest thing since sliced bread. But all of a sudden, there was a rash of 3 or so, 4 maybe, that crashed, and they discovered that in all cases, cracking was initiating in these regions that are in the corners of the windows here. Okay, can anyone, I heard a stab at the correct answer out there. Does anyone know why a window corner might? It's a stress concentration. So it was a high stress region, and that stress concentration didn't immediately show itself. So you load the aircraft once and nothing yielded, nothing cracked. You load it a second time, third time, everything seems fine, and then all of a sudden these cracks are appearing. And that's a fatigue issue. When we load something statically, we may not see it fail, but if we repeat that loading over and over and over again, cracking can initiate. Now, so by a definition for fatigue, so we need a few things to define fatigue. So it's damage done by repeated loading cycles. So it's something that won't happen just from one application of a load. And it needs to be cyclic. It can't just stay at a high level. It's got to go down and up, down and up, and down and up. It occurs for loads much lower than the yield of the material. So if you were to take an aluminium bar and go and test it in a tensile test machine like we have in the solids lab, the expectation would be you maybe get 270 megapascals or so before it yielded. If we cyclically loaded it at 150 megapascals, eventually it would crack, and that's due to fatigue. There's an initiation and a growth, and we'll talk about those processes in a little while. It's promoted by stress concentrations, so it doesn't require a stress concentration, but they promote it because they're local regions of high stress, just like stress concentrations promote all types of failure in materials. And we need some conditions to be met for fatigue to occur. There needs to be some tensile stress for alloys. So if you had a part that was just being loaded in compression and cycling in compression, it won't ever fatigue. So there needs to be some tensile component to the loading. The local stress, right down at the microscopic level, at the grain level, has to reach the plastic range. So for some materials this will happen regardless. Even if you put 1 Newton on them, there'll be some kind of plastic deformation. For other materials that's not the case. So steels have what we call an endurance limit, where below a certain load they just won't fatigue because nothing is changing every time you apply the load. Okay, stress must vary cyclically, which I've already said. Okay, so this is a simple fatigue problem. If we had force being applied to a component, or stress, it probably should be on this axis, I'm sorry, it should probably be stress up there, and time, we can, in a simple sinusoidal case, so this is like you've done in 2400, you've taken a bar, you've put it in a rotating machine with a bending moment applied to it. Now a pure bending moment gives you, if you rotate it, will give you a pure sinusoidal plus and minus load. And in that case, it'll be centered about zero. The amplitude in tension and the amplitude in compression will be the same. That's not always the case. If we have a sinusoidal load, there's nothing that says that the mean has to be 0. The mean can be anywhere. So we define a few parameters that we'll talk about. So stress range is the sort of peak to peak stress. The stress amplitude is the amplitude of the wave. The mean stress is the mean of the sine wave. And max and min are the max and min. But these are not magnitudes. They're maximum on a number line and minimum on a number line. So the maximum positive and the minimum doesn't have to be positive. It can be positive or negative. But the one that's lowest on a number line. Okay, we have to be a bit careful because some textbooks will sort of interchange stress range, stress amplitude, delta sigma. Depending on where you're looking, you've got to be very, very careful that you've used the correct stress range in your formula. I will be very careful about defining it in exams or in tutorial questions about what I mean. But if you're applying it to a problem somewhere else, you've got to be very careful that these are defined correctly for your particular case. Now, if we did this, if we loaded a part with a sinusoidal load like this, and we did it at a number of stress levels. So these horizontal lines represent different stress levels that we might do the test at. And we measured the number of cycles until something fails. As you know from 2400, this gives us what we call an SN curve. Okay, and there'll be some scatter. All the tests won't fail at the same number of cycles, but they'll scatter about a mean, and we can draw a line of best fit through that. Now what this tells us, if we wanted to design a component to last a certain number of cycles, we can go along this axis, pick the number of cycles we want, and then work out the stress level that we can apply to it within a reasonable tolerance so that we hope it won't fail. Okay, it's not 100% guaranteed. There's always some points that will scatter outside of these bands, but we'll see in a minute we can mitigate against those problems. But if we've defined a lower bound and we stick outside that lower bound, everything should be okay. Now here's a made up SN curve for aluminium 2024. It's probably close to correct, but I definitely wouldn't use it to design an aircraft component because it looks very much like massage data, and I know it's massage data because I made it. But if we were to try and use this data for this problem, okay, determine the number of cycles to failure for a small aluminium 2024 part with an alternating stress of 150 megapascals, assume that the material has a scatter factor of 3. And what we'll talk, a scatter factor means a multiple of, if we took the mean from this data, that the range of values, that number of cycles could be 3 times less or 3 times more than the mean value. Okay, so that's what I mean by scatter factor. All right, so it's a pretty simple example. we've got 150 megapascals applied to the component. Okay, we can go to the data. Now one issue, some people have an issue reading a log scale, so we'll go through it here. What's the number of cycles for 150 megapascals from this curve? Yeah, 4 by 10 to the 5 cycles. So what we do is we go across here till we hit the line, which is there. We come down to work out the number of cycles. We can invert that as well. We can use cycles to get stress. Now to read this is 1 by 10 to the 5, 2 by 10 to the 5, 3 by 10 to the 5, 4 by 10 to the 5. Okay, so the number of cycles is 4 by 10 to the 5, or the mean number of cycles. So if we wanted to design a component that was going to fail half the time, we could use 4 by 10 to the 5. If we wanted to design a component that's unlikely to fail, we can divide by the scatter factor, which gets us back to 1.3 by 10 to the 5 cycles. So 130,000 cycles, and we should be safe. Okay, so that might be useful if you were designing an inspection program for a particular component. You could say, I want to inspect it every 50,000 cycles so that if I don't catch it the first time, I can catch it the second time before it fails. So if you knew it had 130,000 cycle lifetime, you could inspect it a couple of times, potentially. Okay, so that's a simple example. Things can get more complex very quickly. So the next bit of complexity for our SN curves.
Can you please go through when you use the scale factor of 3?
Okay, so if we look at this data and we assume this data is a mean of all the test data that we've done. So this says if we use this data, 50% of specimens we tested failed at a lower number of cycles, and 50% of specimens failed at a higher number of cycles. So the scatter factor is it's a way of trying to capture that range so that we act on the conservative side so things don't fail. So a scatter factor of 3 means that if the mean data says if half the specimens fail at 400,000 cycles, if we divide by the scatter factor of 3 to get to 130,000 cycles, that means that we hopefully won't get any failures at that number of cycles. If we kept cycling it from 130 up to 400,000, the likelihood of failure is going up and up and up and up as we keep applying load. Okay, so the next thing that can happen is that we don't necessarily have to cycle things about a nice mean like you did in 2400. We can cycle them in different ways, and this might be due to, say, pressurization of a fuselage. If you think about a fuselage that's getting pressurized, when it's unpressurized, it's got basically 0 stress in it. As it's being pressurized, it goes up to a maximum tensile stress, and then it gets unpressurized and goes back to 0 again. So we can define a term called a stress ratio, which is the minimum stress divided by the maximum stress, and that can help us use different SN curves to get the right data. So if you loaded a material this way and you loaded a material this way, you'll get a different number of cycles to failure. So we need to wrap our stress ratio into our formula somehow.
Is the stress ratio an absolute value or is it positive or negative?
It can be positive or negative. Okay, so it can have a value of up to 1 in the positive direction, or it can have a value down to negative infinity. Because depending on the minimum is often negative, so R can be negative as well. Okay. Now, this is complex data here, which I won't go through in class, but it's in one of your tutorial questions. But basically, this is a two-dimensional representation of our SN curve. So instead of just accounting for the alternating stress, we're accounting for the alternating stress and the mean stress, or the maximum stress and the minimum stress. We've got multiple ways of reading the data, but we're accounting for two sets of axes. And instead of a particular data point on a curve, we now have a line. So this line here is 10 to the 4 cycles, for instance. I'll draw that on the annotation for the people watching at home. This defines 10 to the 4 cycles. Now what that tells us is that if we had an alternating stress of 50 and a mean stress of 0, then we would get somewhere around 10 to the 4 cycles. But if we had an alternating stress of 50 and a mean stress of 40, then we would get much fewer cycles out of our component. So this data can be read in multiple ways, but we've got stress ratio up here at the top. This axis here is minimum stress. Maximum stress. This axis here is minimum stress, and an axis here for alternating and an axis here for mean. But it's all combined onto the one plot, and you can have a chance to use that data in the tutorial question. But it's a way of accounting for the two variables that we need to define how our sinusoidal curve is varying. Okay, so I won't do an example here, but you can ask the tutors about if you have any issues reading this data. Okay. So as I said before, some materials have what we call an endurance limit. Unfortunately, aluminium doesn't tend to have one of these, but steel does. An endurance limit basically says that there's some load or some stress at which the number of cycles asymptotes off to infinity very quickly. So if we load below that load, we can get nearly an infinite number of cycles out of our material. Longer than we could possibly use the piece of structure for. Okay. Now, up until this point, we've assumed that the load being applied to our airframe is nice and sinusoidal. But what about if we had something a bit more complex like this that was a bit more realistic? So in practice, an aircraft doesn't spin around on a nice rotating frame like the test you did in 2400 so that you get nice, even sinusoidal loads. The loads are chaotic. There's bumps and bounces as the aircraft is rolling along the tarmac. Okay. As you go up to altitude or as you take off, there are different stresses applied. If it's somewhere on the fuselage, there'll be varying stresses as you're climbing because the pressure outside and inside the aircraft is changing. As we're flying along, there'll be buffeting from gusts and various fluctuations from maneuvers that the aircraft is doing, and then the same as it's coming back down and as it's taxiing again. So there's a peak-to-peak kind of cycle, which is this once per flight. There's also lots of littler cycles. So how do we capture all that complexity? I'll let you have a think about that, and we'll have a break for 10 minutes, and after the break I'll give you the answer. Before the break I posed this question: how do we deal with realistic stress variation? Now the answer's reasonably complicated. What we have to do is we have to break this down into different fluctuating components, and in practice that's normally done by some form of Fourier transform where you would convert this time domain into a frequency domain to work out how many of each kind of amplitude of event are occurring, but we can do it a little bit more. We can assume that the load can be broken down into a discrete number of different types of event. So in this case, in the example I'll show you, we've got events from taxiing, pressurization, etc. And they all have their own mean stress, stress amplitude, and number of cycles. We work out the number of cycles to failure for each term. So on the table we'll show you in a minute, we need a number of cycles to failure if that was the only type of loading that was occurring. Now we can say that fatigue failure will occur when the sum of all these ratios, the number of cycles for loading type 1 divided by the critical number of cycles for that loading type, plus the second, plus the third, plus the fourth equals 1. So it's saying that each type of loading has its own, is taking up its own little fraction of the total fatigue life. So if we think as 1 as 100%, it's the total life of that component. Each type of loading is taking up its own fraction of that, and eventually it will fail. Now, we can be quite complicated about how we do this, and this is an example from Flabel, I believe, which is one of the textbooks that has been assigned to the course. We can look at different SN data to work this out, but for the example we'll do here will be much simpler than that, and we'll assume that everything's got a mean stress of 0 so that we can use our nice data we had before. Okay, so this is the table of data. I've replicated it here on the board, so I don't need to keep it up on the screen. And we'll use, I won't go through the whole calculation process, but I'll give you an example of how to use it. Okay, so if we look back to our data, we could use this kind of complicated data, which is one of the tute questions, asked you to do that. In this case, we're just going to use this simple data. Now, what we have to do is for each type of loading, we have to work out how many cycles to failure. So we've got a few different loading intensities here, 100 megapascals, 150, 120, and 110. So for each of those, we need to go across horizontally and work out the number of cycles to failure for that type of loading. So let's do that for the first one, 100 megapascals. So if we went across here at 100, okay, hopefully the yellow is showing up. Okay, if we go across at 100 and down to the axes, the horizontal axis, how many cycles to failure is that? 3 by 10 to the 6th. Now, because the scatter factor affects all the number of cycles linearly, we can apply the scatter factor at the end. So if we work out how many cycles to failure for the whole thing, we can then just divide by, or number of flights to failure, for instance, we can just divide the whole thing by 3 because it affects the cycles in a linear way. Okay, I'll get a different pen color and we'll do, we've already done 150. We already said that was, what was it, 4 by 10 to the 5. Okay, I'll do one more. Let's do 120 for instance. 120 is somewhere here. So we could say it's about 1.2 by 10 to the 6. And you can fill out this whole table on your own time. Okay. Now, if what I've got here, I've got number of cycles. I'm going to denote F by, F means flight. So number of cycles per flight. And the number of cycles to failure is capital N. Now, what I need to know is the number of cycles divided by the number of cycles to failure. So, I need another column here, which is number of cycles over the critical number of cycles. So that gives us a fraction of the life that we're using per flight. And if you look, if you rearrange these, basically it's this column divided by this column. So if we've got 20 cycles in one flight and it can take 3 million, then in each flight we're using 20 over 3 million worth of the aircraft's lifetime. Okay, so you can populate this column by that column divided by that column. Now, if you do that and you take a sum of all of those, that gives you in one flight the fraction of the lifetime that you've used for the aircraft. So you've got the sum of the fraction of the lifetime per flight. Now, if we want to work out how many flights to failure, okay, we can multiply by the number of flights, which at this stage we don't know. We know this bit. We don't know the number of flights. And at failure, that equals 1. So to work out the number of flights, we just say F equals 1 over this sum that we've just calculated. And if we want to apply a scatter factor, we can also divide through by the scatter factor. So there's a tute question specifically asking you to do one of these calculations. So have a practice go at that, and you can either ask the tutors this week or next week, and they'll be able to help you out if you've had any difficulty. Okay, so I'll skip forward in the questions a bit. Okay. If you've been thinking a bit about this is a little bit limited though. If you've heard anything about aircraft fatigue issues, often it's reported in the media that a particular aircraft has experienced wing cracking, or the A380 had cracking in the ribs, and the 787 at the moment's just had some production cracking issues. What that tells you is that cracking doesn't necessarily equal failure. So all the SN curves have been telling us so far is that we've said that a crack and failure are the same thing, whereas in most parts, a crack doesn't necessarily lead to the failure of the component. Most parts, if they're designed properly, can take some cracking of a small size before they break into two pieces. Now, the prime example of that, a nice simple engineering example, would be something, a plate with a hole that we load up. If we load that cyclically, then there's a stress concentration here at the edge of the hole, and that stress concentration will lead to a little bit of cracking eventually. Now, those little cracks don't necessarily mean that the part will break into two pieces, but if they get big enough, not necessarily all the way to the edge, but if they get big enough, all of a sudden when the part's loaded, it will just split into two pieces. So we need to have an understanding of how these cracks grow and how long they take to grow. Okay, so SN curves are a bit limited. They can only be applied to certain types of structure, which we'll talk about in a little while. We need to, on top of that, have an understanding of how cracks grow. So let's just go through it from a phenomenological perspective. The first phase is initiation. So there's something microscopic going on. Now that's generally happens around grain boundaries, slip planes, some feature of the microstructure of the material which is leading to damage. There'll be some microscopic form of crack. Now that's not of much interest to us as an engineer because there's going to be millions or billions of those in any given component. We can't detect them. They are occurring all the time, but they're ductile. They're generally a shear type problem. If you did go in there with a scanning electron microscope and find one, it would be at 45 degrees to the principal stress direction. So if you remember back from your tensile tests in 2400, if you had a ductile failure, you got a cup and cone type failure, which was a ductile failure. If you got a brittle failure, it was more of a flat surface, which was perpendicular to the load. So these initiation cracks are ductile. Eventually, a few of these happen near each other and they coalesce into something a bit more macroscopic, something that's going to drive cracking. And that is when it enters the growth phase. So it's more of a brittle phenomenon now. The cracking will occur perpendicular to the maximum principal stress direction. So as I've drawn here, the maximum tensile stress is up and down the board. So perpendicular to the maximum principal stress is across the board. So the crack will grow horizontally in this case. And crucially, the crack growth rate increases as the crack length increases. Now, if a rate is proportional to the magnitude of the variable in question, what do we end up with generally? Something exponential. So in this case, it's not truly exponential. It's actually a power law because the proportionality isn't linear, but it accelerates. So the cracking, when the crack is small, grows very slowly. When the crack gets bigger, it grows faster, and eventually it reaches a catastrophic crack growth speed, and we apply some load, and the crack will just propagate off to infinity, and the part will break into two pieces. Now, that unstable phenomena can be as catastrophic as a ship breaking into two pieces, which happened quite a number of times to these American naval warships that were designed. They had a reasonably poor form of cast iron that they were made from, which meant that they had low resistance to cracking, and the bunch of them just split into two pieces in the harbour. Okay. Again, it's only through these kind of incidents that we actually learn about how materials behave. So thankfully this happened to a ship when it was docked in the harbour and not out in the middle of the ocean, because otherwise a bunch of people would have gone down with it. Okay. So as engineers, we're really interested in capturing this phase, because this top initiation bit, we're not going to go around our aircraft with a scanning electron microscope cutting out bits of aircraft and working out whether there's tiny microscopic things going on. And we really don't want this to happen, because that's going to end up with parts of our aircraft unzipping into two pieces. And as we found out with the Comet, that's not a good thing. So we want to have a really good understanding of what's happening here. We want to be able to predict it. If we can predict it, we get an understanding of when we can schedule maintenance to checks to find these things. Okay, so if we find them, we can repair them. So modern philosophy for fatigue control on aircraft generally relies around finding cracks before they get too big. So we can detect them at a minimum size with a particular detection technique, which we'll hopefully get to at the end of this class. If we don't find them the first time, we don't find them the second time, we don't find them the third time, eventually they'll get big enough for us to find, and we make sure that we've got enough inspections scheduled so that we catch them before they get to that critical size in which they become problematic. Now, if we were to look at one of these broken components, and I've got one in my office which I usually bring, but I didn't today because of the classroom's not really conducive to it. The crack will start somewhere. So this initiation will generally happen at a sharp corner, some kind of stress concentration, and will grow. And if you look at it after it's failed, it'll have what are called beach marks. And those beach marks are caused by stop-start crack behaviour. If you get a sudden overload due to a gust, you'll get a little bit of crack growth, and then it'll stop for a while because the loads will drop back down. And all of a sudden you'll get another big overload due to something, and the crack will grow. But on average, the crack growth rate is given by a formula which we'll see in a minute. But these sort of start-stop cracking events, and the gap between them is getting bigger, because as I said, the crack growth rate gets bigger as the crack length gets bigger. So as we get further and further away from where it's initiated, that's happening faster and faster. All of a sudden, you'll get a rough failure surface where the component is just immediately broken into two pieces. Okay, so we can see that in failed components. Now, how do we predict that? We have to use a combination of a couple of different empirical and first principles techniques. Now, when I say empirical, I mean that it's not predicted from solid mechanics theory. If we went and measured the stress of a material, we can predict the stress in something from first principles. We can work, if it's a bar, we can divide the force by the area. We can measure the stress. It's a fundamental calculation, whereas empirical data means that we've gone and tested a bunch of components and we've just measured the response and we've fitted a curve through that response and said this is about how it behaves in practice. And it means that empirical data we can only apply to problems that are similar to the test that we did to measure that data. We can't apply them to other problems because they won't work. So if A is our crack length, so in this case, if we had a crack growing from the edge of this hole here, we just had one crack. If we had A as our crack length, I'll skip that for a minute, and sigma is our far field applied stress, or if it's cyclic in this case, so it's delta sigma, it's the magnitude of the oscillation. We can calculate what we call a stress intensity factor, and a stress intensity factor shouldn't be confused with a stress concentration factor. They're different things. Now, our stress intensity factor determines our crack growth rate. So our change in crack length per cycle is given by a constant, an empirical constant, which you can look up for different materials, times the change in stress intensity factor to a certain power. And that power, in this case, is just given by symbol m. Now, this is empirical data. This is one way to curve fit that empirical data. You can do that in a number of ways. One of the assignments I'll set will have a requirement to look up some data in what is called the Engineering Science Data Unit, ESDU catalogues. And that has just got stacks and stacks and stacks of test data for all sorts of different conditions. Now, if you look up crack growth rates, there are different ways of doing this formula. This is a simple closed form version, but you can look at it on tables in a number of different ways. So for this particular case, we can work out how long the crack takes to grow from one length to another length because we can do an integration. So if we've got dA dN on one side of the equation, so there's an A here, we've got C, and if we substitute the delta K into the top, so now we've got a formula that's got A on one side and A on the other side. What we're really trying to work out is how many cycles the crack will take to grow from some length to another. So we can switch things around and do an integration, which I won't do now. But trust me, it's a fiddly integration, but it's not a difficult one. You can do it with very, very basic integration rules. If you know the first thing about integration, you'll be able to do it. Okay, so the result is this. So if we think about the crack growth rate, what happens to that formula up here if the crack length is 0? What's the crack growth rate? 0. Okay, so this is not very useful for determining the crack growth rate in parts that don't have cracks already because it can't predict that. You need to have some existing crack. So luckily, as engineers, we can't find infinitesimally small cracks. We can only find cracks of a certain size. So that gives us a starting point. If we say we can find a crack that's 1 millimeter long, we can use that as a starting point for our crack to determine how fast it's going to grow. So if we have AI as our initial crack length and AF as our final crack length, and we want to know how long it takes to go from that initial to that final, we can integrate this and come up with this formula. Now this closed form solution is only valid for the assumption that I've got up here. So it's only valid, this is only correct if this is correct. Okay? If we use a different formula for the top, the bottom is no longer valid. All right, so this looks very complicated, but really it's just substitution. These formulae, these are all terms that we can measure. C and M are empirical values, and delta sigma is the stress that we've applied to our component. F is what we call a geometry factor, which is just a different number depending on the shape of the problem we're looking at. This is something we can substitute into pretty easily. So let's do one of those examples. This is what I was talking about with the ADN being a function of delta K. We had a function here, but that function's an approximation for this growth region here. It's an approximation. In reality, the data is a bit more complicated. So you can use this data from ESDU data sheets to do the crack growth calculation more accurately. And I'll ask you to do that in the assignment. Okay. So let's just do an example. A crack has grown from a scratch mark on a cutout in the fuselage frame of an aircraft. The crack growth is defined by these relations. So these are the ones that we had before. Now, be very careful when you apply this formula because there's some very weird units here. Stress is in megapascals. A can be in meters or in millimeters or in any set of units. Now, so what are the units of delta K? They're, in this case, megapascals square root meters. There's a square root in the units, so it's a weird set of units. And then when we put it in at the top, we then multiply it by a factor that can be anything. In this case, we're going to use 3, but it could be 2.5. So the units of this bracket here would be megapascals to the 2.5 times meters to the 1.25. So that you can end up with some very, very strange units. So all the constants in here have to be empirically based on the value of the units you're putting in. You can't swap out this constant and use pounds per square inch and inches because this constant won't be applicable anymore. The constant has some kind of wrapped up dirty units in it which you can't see because it's come from empirical test data. So in this particular case, we're going to have megapascals and meters, and we'll try an example here. So can you all write down these constants here because you'll need them in a minute. Okay, so if a fuselage is subjected to a stress cycle from 0 to 80 megapascals once per flight, how many flights would it take for the crack to grow from a length of 1 millimeter to a length of 5 millimeters? Okay, so that's it for fatigue for this class. One thing I will talk about is when and where we use these kind of problems. So when we talk about the strength of aircraft components, we tend to talk about two different strength levels. There's the limit strength and the ultimate strength. The limit strength is the strength of the component, assuming that it's the highest load that the aircraft would see in service. So the limit load, so the external loads that we would put on in our load case, is meant to be something that an aircraft might see once in its particular in its lifetime. So the worst combination of load factors and gusts and everything together would be the limit load. And at the regulations say at the limit load, there should be no permanent deformation to the aircraft. So no plastic damage, no yielding, nothing occurring at limit. Ultimate is an extra reserve. It's 1.5 times limit load that we put on top, and that the aircraft needs to, under the regulations, sustain ultimate load for 3 seconds. So it's allowed to have yielding, it's allowed to come down and look like it's bent out of shape, but it has to survive and be able to land after experiencing ultimate load for 3 seconds. Now, if you look up ultimate load tests on something like the 787, you can see these big aircraft that they have to do, and they put an aircraft in a set of jigs and bend its wings up until they get to ultimate load. And if you think a bit of turbulence when the wings are moving around is a lot, the aircraft wings are nearly touching at the top before they snap them off the aircraft. So there's a lot of reserve capacity in these aircraft. Now, that means that everything that we put onto the airframe when it's new has a load capacity that's up here somewhere. It's above the ultimate load. So it won't fail until it gets up there. Now, if we put on this axis time or number of cycles or number of flights or any sort of time-based axes, some things as you load them up will do this. Okay, they'll go from looking completely fine to being nearly under what needs to have limit load strength, otherwise it will fail when you apply a gust load or something to the aircraft. So an example of that might be something that cracks very simply. So high tensile steels, for instance, have very low fracture toughnesses, so they tend to go from having undetectable damage to breaking fairly quickly. Some components, however, if we would travel along, would do something like this. And those components, we have a time window between when we can detect damage. So say we have a detection scheme that can detect when the cracks are growing. We've got a window between when we can detect damage and when we can, when the part becomes too weak. Now, for these kind of components, this window is defined by SN curves. Okay, so those SN curves that we did in the different types of SN curves that we looked at, these, if components fall into this category, they're what we call safe life components. So the classic example that I always tell people is landing gear, but things like turbine blades are also in that category. They're components that are made from materials where we don't get any indication that failure is going to occur before it just happens catastrophically. So what we have to do is when we design the part, work out what life it's going to have at the load, under the loads that we're applying to it. Be very conservative, and then when it gets to its safe life, we just take it off the aircraft. We don't inspect, don't try and find the damage, we just take it off the aircraft. And that's what we call safe life, because we don't have a window where we can find damage. Now, for the things that we can have a window for, this is given by our crack growth. Okay, so those crack growth formulae that we're using, the DADN, for components where we can map the growth of a crack, and that crack growth is a reasonable number of flights. From an engineering perspective, when we're predicting the life of a component, we can use the crack growth formulae to predict that. So SN curves have limited utility for most real aerospace applications. They may give you an indication of when damage may initiate, but for most real aerospace components that have reasonable life, we have to use crack growth formulae. And these components are called fail-safe components. There's some other criteria that they have to be to qualify as fail-safe, but basically the primary criteria is that they need to have a long window between when cracking starts and when it will break the component into two pieces. Okay, so that's fatigue wrapped up. We'll talk now briefly about corrosion before I give you another break. Now, corrosion is the second primary issue that we have with our structures, and as a definition, corrosion is the natural disintegration of material as it's attacked by one or more substances in its environment. Okay, so this is just a corroded pipe. You've all would have experienced something that's rusted, something that's corroded. No one's got to this age without seeing that. So you all have an intuitive understanding of what corrosion is. Okay. Now, more technically, there's two broad categories which we'll talk about. There's chemical corrosion and electrochemical corrosion. Now, chemical corrosion is the type of corrosion that you would have done in high school science, where you drop a piece of metal in acid and it just turns into salts and hydrogen and whatever else. It's a direct chemical attack. If you did higher level chemistry at uni, at high school, you probably would have done electrochemistry, which is setting up a battery. So a battery is corrosion via a different means where you have dissimilar metals. You need an anode and a cathode, an electrolyte and a conductive path, and we'll talk about that in a minute. But it's an electrolytic process rather than a chemical attack. But they're two broad categories, and we'll talk about both of them. Now, some materials, and aluminium luckily falls into this category, and it's one of the reasons it's quite good against corrosion. Corrosion occurs evenly across the entire surface of the material. So aluminium, as soon as you take it out of the processing plant, will immediately start being corroded by oxygen in the environment, and it'll happen very, very quickly. But once an oxide layer is formed, that oxide layer is then very resistant to further corrosion. So aluminium actually comes with its own corrosion screen, I suppose. It's got its own coating on that comes from oxygen in the environment. That doesn't necessarily work beneficially for all materials, because sometimes the oxide volume is bigger or smaller than the parent material. So if it's smaller, once the oxide forms, it'll crack, and then it'll open up more material to expose to oxygen or chlorine or sulfur. Okay. If the volume of the oxide is bigger on the surface, it'll buckle off and crack as well. So luckily with aluminium, the volume of the oxide and the volume of the raw materials are about the same. So it ends up with this nice protective coating generally. That's not always the case. So for steel, which you would be familiar with rust tends to flake away off the surface of a rusting component. That's because iron oxide rust is bigger in volume than the steel that's underneath it. So once it starts corroding, it actually exfoliates and peels off the surface and exposes more iron to rust. So it's a repetitive process. More and more material is corroded. Now, most materials are what we call alloys, so they're made up of multiple materials. They're also generally multicrystalline. So if you look inside a metal under a microscope, there's lots of little crystals of metal, which means that you've got lots of different materials locally. You've got changes in the metal composition from one phase to another. You've got grain boundaries. You've got all sorts of places where corrosion can attack. And the problem with a lot of corrosion is that it selectively takes out one species in the alloy over the others. So you get what's called selective corrosion. And that's bad news generally from a corrosion standpoint. So we can have intergranular corrosion, exfoliation, galvanic corrosion, and stress corrosion. We'll have a look at those separately. Now, intergranular corrosion, if we look here, this is some crystalline metal, and the corrosion has taken out all the grain boundaries. So whatever's in the atmosphere that's attacking this is attacking the species that are at the grain boundaries, and they're turning into a gas or something that can then leave, and it's leaving voids in the material, and that can ladder away and disappear inside the material, and you end up with the structural integrity of that material disappearing fairly quickly. Okay. We can also have a special type of intergranular corrosion called exfoliation, which is particularly bad for aircraft because it occurs for rolled materials. So if we get a material that's been rolled into a sheet or extruded into a stiffener, the crystals in the material, if it's been cold rolled, the crystals are all like big flat sheets. They've been stretched out in one direction. So they're stacked up very tightly through the thickness, but they're quite long, and they're like sheets stacked together. Now, corrosion can get in the end of components and corrode in an intergranular fashion on the inside and cause what's called exfoliation. It's very difficult to see from the outside. All this corrosion can be occurring inside, and the structural integrity can be completely gone. And in most cases, it's quite hard to see from the outside. And when you apply tension to that component, you probably won't notice too much difference because all the grains are still in place. They'll still carry the load reasonably well. If you apply compression to it, it will have nearly no strength. Now, if you pick up your exercise book that's in front of you and load it in tension, you'll get most of the strength of the book. If you try and squish it, the pages will just separate. Is what's called brooming failure. There's no compressive strength in a stack of paper, and that's what happens when you get intergranular corrosion. It loses all structural integrity, and sometimes you can get off the ground because something's loaded in tension, and then you'll hit a gust and it'll be loaded in compression and your part will fail. So it's a dangerous type of corrosion that we need to deal with. Now, galvanic corrosion is selective, but it's also electrochemical. So this is the other type of corrosion that I was introducing at the start. It only occurs in cases where you've got two dissimilar metals or two dissimilar atomic species. Now, one of those will have a higher or lower electrode potential than the other. They'll have a different propensity for taking or giving away electrons to the surrounding environment. And that's how batteries work. A battery is just a bunch of these things stacked together. But we can inadvertently set up batteries on our aircraft that lead to corrosion. One of the species, the anode, will corrode and donate ions to the solution. So we need four things for this to happen. We need a cathode, an anode, some form of electrolyte for the ions to flow around in, and we need a path for electrons to flow. Now this happens nearly immediately. If we stick a steel bolt in an aluminium plate, you've got the perfect conditions for this to occur, because if any moisture gets in here, you've got a nice electrolyte, you've got an electron flow path because these two materials are in electrical contact, and there's two dissimilar metals, and one of them will start corroding. So the anode will start corroding. So we have to avoid dissimilar metals in our airframes as much as possible. Okay, and some examples here where you've had a steel lug for taking a steel pin to take a lug bolted onto an aluminium bracket, and they haven't inspected for corrosion enough, and when they've taken the steel pin off, there's a lot of corrosion in the aluminium underneath. And so generally from a structural perspective, we're trying to avoid mixing and matching metals. Okay. Stress corrosion is a special type of corrosion where things will corrode more if they're stressed more. So for places where there's stress concentrations, they will be the places that will corrode first. It's often called stress corrosion cracking. Okay. Now, what does this mean for us as engineers? We're interested in controlling this. A lot of engineers in Australia especially get employed to oversee maintenance of aircraft fleets. So they don't get on the ground and do the maintenance. That's the work of a licensed aircraft maintenance engineer. But the aerospace engineer will be overseeing the program of maintenance. So we need to work out ways of mitigating against corrosion and make that part of the maintenance routine. And the ways that we can mitigate are to choose materials of the airframe more carefully. Well, that's not really the choice of an aerospace engineer in an airline, but it's the choice of an aerospace engineer when they're designing a component. Isolation of reactive materials, so keeping two reactive species apart or keeping them separate from the atmosphere. Cleaning, so generally any dirt on a structure attracts moisture, and that moisture acts as an electrolyte, so corrosion is accelerated. Inspection and repair, and we'll talk about each of these in a little bit more detail. So, material selection. So, choosing a less reactive material if possible. So, 7000 series aluminium, which is just a type of aluminium that's often used because it has a higher strength than 2000 series aluminium, but it's more prone to corrosion. So if we're in a situation where corrosion is likely, we would use 2000 series instead of 7000 series. There's just a different set of alloying components which makes it more susceptible to corrosion. Composites in general are less susceptible to corrosion than metals, so if there's a situation where corrosion is really critical, we might consider switching to a composite part instead of an aluminium part because it's less prone to corrosion. And don't mix and match materials if possible. It's okay at very localized regions. Quite often there'll be a mixture of materials at a wing lug or something where it's easy to inspect, but you don't want a fastener and a sheet of material on your millions of fasteners and your panels to be different materials, because then you've got to inspect millions of different locations for corrosion. Okay. Material isolation, if anyone's ever been inside an aircraft that hasn't got all its internal paneling in, they'll see that everything's green. It doesn't look grey like normal aluminium, everything's painted green, and that's because they use a zinc chromate isolation paint, and that paint serves two purposes. It isolates the aluminium from the environment, so it makes it less susceptible to corrosion. It also acts as what we call a sacrificial anode. The zinc in the paint will corrode before the aluminium does. So if you repaint every now and again, the aluminium underneath won't corrode, but the paint potentially will. So you just scrape the paint off and put a new coat on every time you do a D check for the aircraft. And cladding is another example. Some materials come with another very, very thin layer of another material sandwiched on the top, and that's what we call cladding. Anodizing is a way of coating, painting, primers, organic coatings. But most aluminium components are on this, painted like this. Okay. Electrolyte control. So one of the things that generally causes most corrosion in aircraft is moisture, and it's the electrolyte. One of the simplest ways of breaking down any electrolytic corrosion is to take one of the four aspects away. So you can't get electrolytic corrosion unless you've got anode, cathode, electrolyte and electron flow path. It's very hard to get rid of the electron flow path. Your cathode and anode are determined by the materials that you've got. So the easiest thing to control is the electrolyte. So if you can keep moisture away, you'll keep corrosion away. So sealing joints, regular cleaning, picking your geometry carefully so that any moisture inside the aircraft doesn't get trapped in a place where it will lead to corrosion. It will run to a drain where you can get it out. So there's a lot of things you can do to control the moisture inside an airframe. Okay, and like cracking, corrosion accelerates with time. So a little bit of corrosion will grow very slowly, but corrosion will lead to further corrosion in an accelerating fashion, just like a crack will lead to a faster crack growth. So if you can catch the initial bits of corrosion, you'll lose much less material than if the corrosion is in its late stages, you're going to have to rip the whole part out and put a new one in. If the corrosion's in its very early stages, you can remove it and re-isolate the material and you'll be fine. Okay, so corrosion-prone areas, bases of bulkheads. So bulkheads are dividers in a wing or a fuselage that separate one part of the cabin from another. And bases of bulkheads, moisture will often pool up against the base of a bulkhead. Galleys, so underneath any wet areas, but toilets, galleys, near batteries. Obviously batteries have corrosion, they have acids in them often, so any leaked acid or acid vapors can corrode. Any loose fasteners, because loose fasteners allow moisture in more easily than a tight fastener. But you can use common sense here. Anywhere where there's a place where moisture can get trapped or where you've got potential for corroding elements like acids to attack the material, they're places we need to inspect. Okay, and one other thing which I'll introduce is called the activity series. Now, things that are least likely to corrode are at the bottom here. They're what we call the most cathodic species, and at the top are the most anodic species, which are the ones that are most likely to corrode. Now, if you put two materials together that are very close on the activity series, they won't form a battery. The electropotential between them is too low. If you put things that are far apart on this chart, you will get corrosion. Now, you can see here that the aluminiums are all fairly high up there, and the reason that aluminium is okay for corrosion because it kind of self-protects itself with its oxide layer, but if you do get exposed aluminium, it's very reactive. So if you were to put an iron fastener in a 70-75 panel, there's a big gap here on the activity series between those, or steel fastener. There's a big gap there so that corrosion is likely. If you were to put an aluminium fastener in a 70-75 panel, the gap is much smaller. Now, for instance, with carbon fibre, the reason that that carbon fibre is so great at corrosion, or composites, are that carbon's way down the bottom, so it's really unlikely to corrode. But we have to be careful with the fasteners that we put in it, because if we were to put steel fasteners in a carbon fibre structure, all the steel fasteners would corrode away. So we have to go as far up this chart as we can, and we often put titanium fasteners in carbon fibre structures because they're as close as we can get on that table with a reasonable material property. All right, so we'll talk about wear, which is the second last of our aging mechanisms. I won't go into any analytical detail with wear, I'll just talk about what it is. Wear is a surface removal of material. So we're talking about the slow removal of material from a surface by mechanical action. So you all would have experienced wear if you've looked inside an old set of bearings, or if everyone as a kid probably kind of like scratched a scratch sticks on the ground and things to make sharp points. It's wear. If you're taking one thing on, if you rub one thing against another thing and material disappears, you've worn something out. So everyone sort of has an intuitive understanding of what it is. In practice, in an aircraft, it only happens when there's two parts that are moving relative to one another. Surprisingly infrequent on an aircraft. There aren't that many places where two things are moving relative to one another. And that it's proportional to the normal forces that are applied. So bigger forces equals more wear, smaller forces equals less wear. So more friction is higher wear as well. Okay, it's a few categories and I'll talk about some of them. Abrasive, adhesive, chafing, erosive and contact stress fatigue. I'll only talk about a couple of them because they're the most important ones. Abrasive wear is where you get two bodies and you get something stuck between them. So anyone who's used sandpaper knows about abrasive wear. So if you've rubbed something with sandpaper, it's the particles of the sharp sand that get stuck between the two objects that create the wear. It removes material from one surface or the other. Now, the particle doesn't have to be something completely foreign like sand. It can be a previously broken piece of material. So if there's some other piece of worn out material floating around in the system, that can act as the abrasive component. So like most of the things we've talked about so far, wear can lead to more wear. So a little bit of wear, you'll get some debris, that'll lead to more wear and more wear and more wear. So all of these things tend to act in an accelerating fashion. We have to worry about the rate at which these things are occurring. Now, the other type of wear is what we call adhesive wear. So when there's a normal load applied to two components, especially alloys, at the microscopic level, right down at the grain level, there is some fusion between the two parts. There'll be some metallic bonding, so there's an adhesion there. And as you keep moving one part relative to another, you'll end up with a part detaching from one side and attaching to the other side. And eventually, because the strength of that bond is not very strong, eventually that part will just break off completely and float around in the system. But the two, adhesive and abrasive wear, account for most of the wear that we'll be concerned with. And they can lead to, adhesive wear can lead to abrasive wear as well. Okay. Now, wear is mostly common in things like linkages. So where we've got a spherical kind of cup joint in a control linkage, there's a lot of these in an aircraft. They're relatively easy to inspect, luckily, but there's quite a few of them working control surfaces. So every time you move the stick from one side to the other or up and forward, your control surfaces are moving, and those control surfaces are pushed in and out by push rod linkages, and they all have these cup and ball connections on the end. Now, they're generally not lubricated. These things are just free running in there. They might have bearings in them. Or a Teflon, but those things can wear out because they're constantly moving relative to one another. Now, the problem with wear is that the biggest problem with wear is not that the material's being removed. That is generally a relatively small issue. The biggest issue with wear is that it generally leads to slack in the system. Wear will reduce the stiffness of a particular linkage chain. So when in a small aircraft, if the pilot pulls on the stick and there's a bunch of connections that are made, that the yoke might go to a push rod, and that might be connected to a cable, and that cable might run through some pulleys and then back to another control linkage that controls the control surface. So there's a lot of connections in that system. And if those connections start to wear, they all have a little bit of free play in them. They all get a little bit sloppy, so that you end up with the ability for there to be chatter in the control surface. So even if the pilot's holding the stick still, the control surface has some free play in it because there's slack in the system. Now, that's a problem because for two reasons. Just the vibration of it in the airflow will cause fatigue, and also can lead to a more catastrophic phenomenon, which is called flutter, which we'll talk about right in the last lecture of this semester. And flutters are a forced oscillation where the airflow will actually push the control surface one way or another and will get bigger and bigger and bigger. Much like if you keep pushing a kid on a swing in the same direction, you'll end up, the kid will eventually get so high it falls off, or it'll do a full circle. If you keep pushing something in the same direction as it's moving, the oscillation will get bigger and bigger and bigger and bigger and eventually break your control surface clean off the aircraft. And that sounds unlikely, but it's actually very, very common. It's a problem that you have to put a lot of design effort into the aircraft to stop it from happening. And free play in linkages accelerates the rate at which that flutter will occur. So we try and avoid wear in those settings. Now, wear formulae tend to be entirely empirical. So you tend to have what's called a wear volume. This is often taken, the time derivative of this, so the wear rate, if you put a W dot on top of this and you put a V here instead of a distance, you've got a time derivative. But the wear volume is proportional to some empirically measured experimental constant times the normal force times the distance of slide. So if you slide something further, it'll wear more. If you apply more force, it'll wear more. But there's also a constant in there that accounts for the type of material. And if you're looking at the time derivative, the wear rate will be proportional to the velocity. All right. And in practice, these are tricky to use because you've got to do a test that's similar enough to the type of problem in the aircraft. And these are really only empirical formulae. Okay, so the last one of our 4 aging processes is creep. Okay, so creep used to be a big issue for aircraft, and it's not so much anymore. Creep, sometimes referred to as stress rupture. So if you see stress rupture in a textbook or a paper somewhere, they mean creep. It's the slow, gradual stretching and rupture of material through a constant load. So if you took a piece of plastic and you sort of held one end and you applied a mass to the other end, if you held it for long enough, eventually that plastic would draw out and snap, regardless of how low the load is. The time it takes to do that might be astronomically high, but it will creep. And it will be accelerated by temperature and the amount of load applied. So if we do a time versus strain on an axis, we'll generally get one of these kind of runaway curves that you've seen in other places. So it turns out that most aging processes are accelerating. They get faster as the thing gets worse. Okay, so because it's elevated by temperature, it used to be an issue for rotating components in engines. So if you have a turbine blade inside the core of a jet engine, might be at elevated temperature, and it's spinning constantly at 2400 RPM or somewhere about that. So if you've ever swung a rock around your head on a string or a tennis ball or something, there's tension in that cable. And because these things are spinning, they're constantly under a tensile load. And they're at a high temperature. So they are susceptible to creep because they're under a constant load and they're at a high temperature. Now, there was a rash of aircraft that were failing this way during the first Gulf War because they used older alloys for their engines, and they were kind of old Cold War era aircraft that were being asked to go a bit too hard during the Gulf War, and they were failing this way. Modern day jet engines don't tend to be a problem because our alloy technology has got better. We use what are called super alloys that have big single crystal superalloy structures or amorphous metals that have very low susceptibility to creep. So you can put them through a very high temperature and very high loads, and they're very unlikely to creep. So it's a problem that has almost been erased from aircraft is creep, but it's still around. You still have to account for it. But if through clever design, we can almost eliminate creep entirely. Okay, so as I said earlier, right at the start, I said that the material that we use for our aircraft will have to be matched to the mission of the aircraft. And we'll talk, now that we know how aircraft age, we have more of an understanding of why that is. So this is one of our old UNSW aircraft. This thing used to be parked down beside the mech building many years ago. And this is a, what is it, a 787, I think? No, I can't say it well enough. Okay, these two aircraft have very, actually I don't think it is a 787, I think it's probably a 73. Very different missions. This thing spends a lot of time on the ground. In fact, the one that was parked near mechanical engineering spent years and years and years parked on the ground not doing anything. They tend to be outside a lot. They don't fly all the time. Whereas this thing is, as we've already discussed, maybe doing 6 to 12 flights a day, depending on the type of hop it's doing. And it's up and down and up and down and up and down. You can understand then that these two are going to have very different requirements in terms of the materials that they're going to be made from. This aircraft is not going to be anywhere near as susceptible to fatigue because it's not doing that many flight cycles. It's going to be much more susceptible to corrosion because it's exposed to the elements, it gets more moisture applied to it. Corrosion is going to be a bigger issue. These aircraft are doing so many flights that fatigue is the dominant problem. So we have to match materials to the mission. Okay, so a particular mission might be ground, takeoff, cruise, some kind of operation, and then landing. Okay, and depending on how many of those cycles we do, we'll need to choose different materials. And also we have different cost drivers. So light aircraft, the initial cost is important. Someone has to go and dip into their pocket and buy a light aircraft for $100,000, $150,000, whatever they're paying for it. It's like buying a car. And the initial cost is important. They tend to use airframes that are much cheaper. Occasionally they actually use steel in their airframes because it's very easy to make empennages in these kind of structures out of steel. And the initial cost is much more important than the operating cost because they generally don't get operated that much. They're more of a, they're quite often used as a recreational thing and it doesn't really matter how much it costs to operate them. A biz jet is the next sort of step up. Generally, the initial cost is a little bit less important. They might be operated nearly as much as a commercial aircraft, so operating costs do become important. Biz jets are a bit unique in the fact that they tend to be a place where high performance materials are trialled out. There's a lot of designs out there that are all composite, which is rare for aircraft to be all composite. It's because it's a little bit of a luxury category. I think they can get away with trialling a few more things because they get to charge so much for the airframes. Now, on the other end of the spectrum, something like a civil transport aircraft, the initial cost is nearly insignificant. It's not insignificant, they're still hundreds of millions of dollars in some cases, but that cost gets wrapped up into the lifetime operating cost of the aircraft. And if you think that this thing is going through, if it's a long haul 747, it might be doing 2 flights a day. If it's a short haul 737, it might be doing 5 or 6, 8, 10 flights a day. You're potentially burning $200,000 worth of fuel every day. So the fuel burn and the operating costs and the maintenance costs and all those things that are lifetime costs of the aircraft become a really big consideration compared to the initial cost. So anything we can do with these aircraft to save weight using higher performance materials, using things that are a little bit more exotic on the airframe to achieve a lower weight, we will do. And the next step again, which is a little bit more performance demanding, is military aircraft. So they're very performance driven, don't care so much about operating costs, but they're after not just efficiency, but the best performance possible. So weight comes into that calculation because they need to be nimble, so the lighter they are, the more they can accelerate. But they tend to have extensive use of composites because they're very, very demanding of that last bit of performance that can't be achieved from aluminium in some cases. Okay. We also have to think about where the sources of fatigue come from. With civil transport, it tends to be takeoff and landing, or takeoff generally, where most of the fatigue occurs. If you think about an aircraft throughout its flight cycle, it's fully laden at the beginning, but by the end it might be 30% lighter because it's burnt all its fuel. So the loads when it takes off are generally higher than loads when it lands. Also, the act of climbing means you have to apply a higher load than when you're cruising, because one's accelerating and one's straight and level. The other issue is that most gusts happen in the lower level of the atmosphere. So once you're cruising, the air's pretty clean and you don't tend to get as many gusts, so the fatigue loading from gust loading is much lower. So for civil, the vast majority of the fatigue problem comes in that initial takeoff phase. Military, depending on the operational phase, that can be pretty demanding as well. If you imagine that you're putting a fighter, in this case, through some form of combat maneuver, you're really pushing the limits of the airframe strength, so you're putting a large amount of fatigue load on the aircraft. There was a story from, I believe it was the Vietnam War, where a lot of aircraft were coming down with extensive wing cracking and they lost a few bombers from fatigue cracking. And the reason was that the manufacturers were hauled before Congress basically to say, why are all these aircraft failing? We didn't pay you for dud aircraft. And they effectively said they were never designed to drop their bombs, because most military aircraft don't actually drop their bombs very often. And because Vietnam was a horrible conflict where they were dumping lots and lots of ordnance on the ground, they were going up with ordnance, and then when they release them, the wings are in a different loading condition. So there was a huge fatigue load every flight, and they weren't actually designed to drop ordnance that often. So sometimes the operation is actually not what you expect it to be. And also lifetimes are different. So an aircraft that is civil might need 100,000 hours for a lifetime, potentially more, whereas military aircraft may only have 10,000 hours operating. So military aircraft tend to spend a lot of time hanging around waiting for things to happen, and then when they do, they're really high exertion, whereas civil are the opposite way. They do a lot of action, but it's not very taxing. You won't ever see a civil aircraft do a 2G turn, whereas military aircraft are doing them routinely. So there's different issues there. So we have to choose different materials. I won't go into too much detail on these following slides. I'll put them up in the notes so you can look at them in the notes. But even if we've got an all aluminium aircraft, there's thousands of different types of aluminium we can use. And in this example here, we can see that the different aluminium usage in different parts of the aircraft. The wing surfaces, the lower wings are 2000 series aluminium, and the reason that is because lower wing skins are more prone to corrosion. If you think they're at the bottom, so any moisture pools there, so they're more prone to corrosion. So we use a corrosion-proof material. Places where they're less prone to corrosion, so the top of the wings, because water won't pool there, we tend to use a higher strength grade of aluminium, a 7000 series aluminium. So even in something that we would call an all aluminium airframe, we can have a lot of different choices of material, and I won't go into too much detail with that. Again, this is really for reference rather than talking about in class, but there are different heat treatments and tempers and things that can be applied to aluminium. So when you see a code for an aluminium alloy, generally the code will be a number, a 4-digit number that'll start with a 2, a 6, a 7 or an 8. Aerospace is normally 2000 or 7000 series. Then they'll have a T something afterwards. So T3 is solution cold worked and natural aging. T4 is solution and natural aging. So the different temper treatments are something that they've done to it to change its material properties. So you have to, if you want to specify a material, you specify the alloy and the treatment that's done to it. Okay. Now, again, I won't go into this in too much detail. Okay, so we've got a little while. I want to quickly get on to some non-destructive inspection. So if we've got an aging airframe, when we look at an airframe from the ground, which they do before every flight, someone walks around on the ground and goes, "No, can't see any cracks," tick a box. And if it's a Qantas flight, it's an engineer that does that. If it's a Virgin flight, it's flight crew that does that. If it's Jetstar, it's like the cook, maybe, I don't know. They walk around and say they can't see any cracks, but we can't really. That's just eyeballing it. We can't see cracks smaller than, I don't know, a few millimeters. Maybe something needs to be 50 millimeters before you're going to see it up on the tail of an aircraft from the ground. So we need better techniques to be able to see cracks, and we need techniques that can also look inside. We don't want to have to do everything from the outside. We need some way of penetrating into the structure to find potential cracks. So, and we also need them to be non-destructive. So that's why the ND is here. We can't go chopping a piece out of the aircraft to go and test whether it's got cracks in it, because then we've defeated the whole purpose of inspecting. So non-destructive inspection is what NDI stands for. Okay. So NDT is also called NDT, non-destructive testing. Okay. Now, one of the simplest ways that forms of NDT is what's called dye penetrant testing. So generally, if you get a piece of metal, if we look at something like a bar that's been bent, okay, when it cracks, generally cracks under load. So there'll be a crack open up on the surface. Now, when it's unloaded, when we put it back on the ground, those cracks tend to close back up again. So they're very, very hard to see with the naked eye. So you've opened a crack, and then it closes back when it's unloaded. So someone's walking around trying to find a crack or looking inside the wing, it's hard to see. So what we use what's called dye penetrant testing. So we have a very low viscosity fluorescent dye that we paint onto the surface, and I'll show you this graphic of this in a minute. And then we apply what's called a developer to draw the dye out of the cracks again so we can see where they are. And we make it fluorescent so we can more easily detect it with a fluorescent light. So difficult to see crack, we paint a dye penetrant onto the surface. So remember, we don't know that there's a crack here, so we just go along and paint the whole surface. Okay, so if there is a crack, some dye will run into that crack locally. Then we wipe off all the dye, and apply, so at this stage there's no dye on the surface. Then we apply what's called a developer, which sucks a little bit of the dye back out of the crack. And then we can walk around with a UV light and shine it on the part. And if there is a crack there, that dye will be fluorescing, so we'll be able to see it quite nicely under our UV light. So it's a way of increasing the detectability of cracks, but they need to be cracks that we can do this process. We can't get everywhere on the aircraft to do this process. So it's useful for some types of cracks, but not others. Another technique is what's called magnetic particle inspection. So if you apply a magnetic current or magnetic field to a part, if there's a defect, it will distort the magnetic field. So if you apply a magnetic field to something and then sprinkle iron filings on it or some kind of magnetic material, they will tend to distort around cracks. So you can see that there's something going on inside because the iron filings will have a weird pattern around where there's damage. And it also can be used for subsurface damage. Whereas the dye penetrant testing, we can't use it for subsurface damage because the dye won't go into subsurface cracks. This will pick up limited amounts of subsurface damage. One that's commonly used for composites, because composites we'll see later are laid up like sheets and glued together. So one of the primary ways that composites fail is that they will have a delamination crack inside. There'll be an internal flaw between the layers, and one way we can detect that is using what's called ultrasonic inspection. We bounce an ultrasonic wave through the component, and it bounces off the back face. So the wave leaves the detector here, goes down, bounces off the base and comes back up again, and is received. So emitter and detector in the same tool. Now, if there was no crack there, the initial pulse would register, and then the reflected pulse would register, and we'd say there's no crack. Now, if you pan along and then all of a sudden there's another peak, that peak is because some of the sound is bouncing off a crack and coming back in a shorter time period. So it takes a bit of a skilled operator to use, but you can go along and detect internal flaws in the material using ultrasonic scanning. And in fact, every composite part that comes off the production line will be completely scanned before it goes onto an aircraft. So actually, they can do this in a production environment with water jets. They have water jets that squirt on either side of the part, and they have an ultrasonic beam going through the water jet, and they will scan each and every part that comes off the production line will be completely scanned for internal flaws before it goes on the aircraft. So it's a way of checking for internal damage, which is generally very hard to see. Okay, you can X-ray components. Now, you can X-ray and find voids, just as you can X-ray your bones in your body, but you can see subsurface damage, which is a benefit, but can anyone think of a drawback of X-raying aircraft? Yeah, you've got an X-ray source. So, and to get through, if you know that denser materials are absorb X-rays more, to get through a metallic sheet, you're going to need to have very high intensity X-rays. So you're going to have this crazy powerful X-ray source floating around, pumping out X-rays, and X-rays just don't stop because they feel like it. They will stop if they're absorbed, but the ones that miss your target are floating off to hit anyone else who's walking around as well. So it needs to be done in fairly controlled environments. So you've got to be careful with radiography. Okay, eddy current testing is similar to magnetic field testing. You can detect changes in the eddy current set up in the material by defects. So an eddy current is a looping electric current set up by an oscillating field, and you can detect changes in that signature if there's a defect. Again, requires a very skilled operator to use, because all sorts of different features will have different responses under this eddy current. Okay, acoustic emission. This is an interesting one for what we call real-time structural health monitoring. So most of these techniques are for detecting damage after it's occurred during an inspection. Acoustic emission is a technique that's been developed to detect damage as it occurs. So you put little microphones on the structure, and if a crack does occur, that cracking has a particular energy release. If the cracking's big enough, it will release a sound. And if you can detect that sound, you can even locate it in space by having multiple microphones. The time delay to get to different places, you can work out where it's going to be. So it's still in its infancy. It's not really applied on big aircraft, but people are looking at ways of detecting damage as it occurs. The weakness of this is that once it's occurred, it's no longer a useful technique. You can't scan a part with this technique after the damage has occurred. Thermography is another one where you have a heat source and an infrared camera, and you heat the component and turn off the heat very quickly and film it with an infrared camera. And as it cools, if there's subsurface damage, that will cool at different rates because there's a flaw or something internally, and you can detect internal damage by filming the part as it cools. This is actually quite a useful technique for aircraft because it's sort of non-contact. You can do it from a distance. You have to be able to get at the part. You can't do it for internal components very easily, but it's quite a useful technique. This is one. Comparative vacuum monitoring is an Australian invention. It uses two arrays of tubes that have got vacuum in one set of tubes and atmospheric pressure in the other set of tubes, and they're applied. They come like a little sticker, and you have a sensor on the end, and you apply them in places where you think cracking is likely, like around the edge of a hole or something. And if there's a crack underneath, then it will link up a vacuum tube and an atmospheric tube, and you'll get pressure change. So you can put, by the sensor you've put on the end, you can detect if there's a crack that's formed underneath the sticker. This is an example. So the little sticker that's applied has these tubes that are connected to the surface of the material. And some of those tubes, which are shown blue here, have vacuum pressure. Some of the tubes which are red are just connected to atmosphere. Now, if in one of your vacuum tubes you start picking up a pressure that's not vacuum, you know some air's leaking in, and the air will leak in from the other part through the crack. So it's a way of just seeing whether there's a crack in the surface of the material. Okay, and the last slide for the day. Now, this is just a summary of all these different techniques. Obviously, they all have their different uses. There's no one-size-fits-all solution. They all detect cracks at different lengths. They all have different capabilities. You don't want to be shining X-rays at people all the time, or you can't walk around just eyeballing every crack because they're all different. So the simplest one here, which I didn't talk about before, which is actually reasonably useful in some cases, is called a tap test. And a tap test is as simple as walking along and going, sounds different than it did yesterday. And a skilled operator can actually detect damage of 40 millimeters. Sounds like big damage, but in some components that's not unheard of. And it's a very quick and easy thing to do. Famously, it was used in Alcatraz, where they used to walk around tapping the bars of the prison to check whether people had been filing through the bars, because you can detect the sound difference between a complete bar and a non-complete bar. But obviously the rest of them we've talked about here. They all have different detection sizes. They have different costs for operating and everything, so there's no one size fits all. Okay, thank you. I'll see you all next Monday.